So your question on the log rank will become hopefully clearer with this. So in the first session, we talked about where survival comes from, what is the survival function, what is the hazard function. And the Kaplan-Meier estimate is a Kaplan-Meier estimation of the survival function. Okay? But we also mentioned that we are interested later on in modeling the hazard. That's why we talked about survival and hazard. But the other thing that people are always interested in is comparing two groups on what? On their survival function. Okay. So we'll talk about that in this session. So we're testing is when we're comparing survival functions. And then we'll talk about how we go about adjusting for covariance. Okay. So we'll talk about first how we test it, and then how we go further and incorporate covariance into survival analysis. Okay, so key point to ma'am over there is that it's hypothesis driven. It's not looking at the data driven. So when I'm testing anything in statistics, I have to have a priori some hypothesis at which I'm testing. Okay? And typically, when we say we want to compare two groups, there's three ways we can do it. We can do it descriptively, analytically, and inferentially. Everybody thinks that the only way to compare two survival curves is to do the log rank, or do a Cox model, or give a p-value. That is the last thing you should be having on your mind when you're comparing survival distributions. You're comparing the survival distributions, compare them. Don't rely on what I call the statistical crutch of a p-value. That's the worst thing that people have taught non-statisticians, but that's the focus of research. It's the wrong thing to do. And hopefully I'll convince you after these next 30 minutes, 40 minutes, that what you should be doing when you're comparing. So if you're comparing two survival curves, descriptively, you're comparing the Kaplan-Meier plots, okay? How do you do that? Look at it. Your eyes tell you, oh, this is going fast here, they're different, they're crossing, this is happening. You may plot the Kaplan-Meier, or you may plot 1 minus the Kaplan-Meier, which is the cumulative incidence function. Either way, you can talk about them. Oh, this one, their event rates are very high initially, they're going low, they're doing this, they're doing that. We will talk also that at some time points, when you have competing risks, you have to use the Allen-Johansson cumulative incidence function. You cannot use the Kaplan-Meier cumulative incidence function. We'll talk more about competing risks. It's something that has not been usually understood by many people, but it is why we have informative censoring comes from competing risks. Okay, and we'll give a little bit more example of that. But descriptively means what? It means using words, your own visual appreciation. What's happening where? What's the hazard? What does the survival look like? Is it fast here or is it slow here? It's what is happening. These are words that you use. Then you can use your own clinical judgment to try to explain why you see what you're seeing. And my experience with most physicians is they're fantastic at coming up with explanations of what they're seeing. Okay, so I'm sure you will be able to do that very well. But then comes analytically. So people don't want just to rely on your words. They want you to give me numbers. People like numbers. So analytically is getting numbers. So they're not satisfied with that. So we give them the hazard rate ratio. And we'll talk about what that hazard rate ratio comes from, how you do it. People call it the HR, but that's not hazard rate, it's hazard ratio. The word that you're dropping is the rate. So it's hazard ratio as opposed to hazard rate and HR. And then you give uncertainty around it by giving the confidence interval. So you're given a number, and you make people happy because now you're not just given words and plots, you're given numbers. People are not happy alone with numbers. What do they want? P-values. So we had to come up with P-values for these numbers. Okay? So we will do the Logrank test statistic, which will tell you how it comes from. And that's an unadjusted comparison of the two curves in their totality throughout the whole profile, as Dr. Jayasilan was saying. But if you also have, wait a second, I have the placebo group and I have the intervention group, but there's males and females in both of those. Maybe the relapse of males is different than the relapse of females with the intervention, without the intervention. So can I do the Kaplan-Meier curves separately for males and for females? Of course you can. The software will do it for you. Now you have 4 curves to look at, and you have the 2 for males and the 2 for females. You can do that. And you can note the difference. You can compare them descriptively. You can compare them analytically. Oh, but you say, wait a second, but there were older people here. There were less younger people there. There were people with advanced stages of their cancer when we initially got them in remission. So now I have people with grade 1, 2, 3 cancer, and I have this, that. I have only 21 people. How can I handle so many different potential stratifying variables? Now I have one person experience here, one person experience here. Or if I have a bigger study, I have 10 people here, 20 people here. It's still not enough. So when we want to look at handling potential variables that may impact what I'm observing, then we are forced to do other ways of adjusting for regression. And we have proportional hazards models, and something that people do not really know very well, but I'll tell you about it because it exists. It's accelerated failure time models. We don't use those as much. Why? Because they're not so easy to interpret. And it's modeling the survival as opposed to modeling the hazard. And remember what I said earlier, we model the hazard, we study the hazard because of its mathematical simplicity properties. Working on the survival, it's problematic because it's an integration thing, while this one is, you don't have to integrate. So we'll talk about this before lunch. Okay. So remember, this is that curve we had. So we can compare these descriptively over time, or if I have pre-specified at a specific vertical point or a specific horizontal cut. So I said, my test, I a priori say that there will be more people dead or relapsed in the placebo by 50% of the time, such and such time, 12 months. Or 50% will be more time will occur later in the intervention. But a priori, you specified it, you could compare them. Or inferentially, we're going to do the test either pre-specified or over time, and we'll calculate the hazard ratios. Okay. So you've seen this graph before. So now we assume the hazard rate ratios are independent of time. We'll have proportional hazards, and that's why we report a single hazard ratio and 95% confidence. So here, they were not happy with just presenting us the plot. What did they do? They gave us analytically a hazard ratio. But the hazard rate ratio is changing over time. Why do they report only 1? How did they decide that they only wanted to report 1? Where did they get that 1? So we'll tell you about that. And then they give a p-value because they a priori had a hypothesis for that p-value to test them overall. We'll talk about where that came. That came from the Logrank. This probably came from the Cox model. So we'll talk about those two ways of comparing those plots. All right. So this is the comparison of two survival curves done by every log rank test that is out there. Every paper that you see, they say we use the log rank statistic. First of all, it's not log space rank. You're not taking the log of the rank. The word is log rank together. It's not hyphenated. It's not two words. It's one word. The statistic is called log rank. And so what we have is that every time there is an event, not when there is a censoring, every time there is an event, remember was when the curve changed. If it's a censoring, it stays flat. But every time there is an event, there is one. We had 17 different events. So every time there is an event, overall for the combined sample, and each one of those, you can find out how many people are continuing to be at risk in group 1 and in group 2. And out of those, how many get an event out of those at risk, and how many get an event here out of those at risk. And so whenever you see a 2x2 table, you can do a chi-square test. Or better yet, you can do a Fisher's exact test. You know the difference between Fisher's exact test and the chi-square test? Does anybody know that the Fisher's exact test uses the same chi-square statistic that the chi-square test does? So the chi-square test uses the chi-square statistic and calculates an approximate p-value using the chi-square distribution. Fisher's exact test uses the same chi-square statistic, but calculates a exact p-value based on permutation principle. So the Fisher's exact test is, in my opinion, the default preferred method of calculation, because I want it, if I'm going to get a p-value, I might as well get it exact. The approximations work when you have large numbers. So if you have here 21 and 21, I would never use a chi-square. I would use definitely the Fisher's exact. If I had 200 and 200, I would still use Fisher's exact test. If I had 2000 and 2000, I'd still use Fisher's exact test if my software will handle it. Sometimes the software cannot handle too many observations. If I had 20,000, I'm sure the software will not handle. That's when you use the chi-square. But anyway, so I can calculate a chi-square statistic at each time point. I can do a 2x2 table. I can get the chi-square statistic at that time point. Therefore, I can see if there's a difference at that time point. But my hypothesis is not at that time point. My hypothesis is overall. So I calculate, if I have M for our case was in the Anderson data was 17. So I have 17 2x2 tables. So I'll have 17 chi-square statistics. I need to combine them. Okay? So the log rank test is, the hypothesis is that the hazard in group 1 is the same as the hazard in group 2. The alternative, or the null hypothesis is the same, and the null alternative hypothesis is that they're different. And under the null hypothesis, this is like every chi-square statistic, you calculate the expected value under the null hypothesis, you calculate the variance of it, and the statistic is the chi-squared with 1 degree of freedom. You don't have to worry about this because nobody does. It is in all the softwares. But the concept is that every chi-squared statistic is taken the observed frequencies and the expected frequencies, and then you're going to standardize it by the variance in this case. But the proposal of the way to standardize this, combining all of those chi-squared with 1 degrees of freedom, was the log rank statistic. It was developed in the United States by Cochrane and Mantle and Hensel. It was developed in the UK by Richard Pito and his brother. And so depending on which paper you read, if it's from the UK, it's the Pito log rank. If it's, you read it from the United States, it's the Mantle Hensel log rank. Some people call it the Cochrane Mantle Hensel log rank. Some people call it the Pito log rank. Best thing is just call it the log rank. Okay? Don't get into trouble politically. All right. But the problem with the Logrank statistic is the one that I mentioned in the break. That is, what it's doing is it is taking each of those separate chi-square statistics at all time points and combining them. But I would like to not use so much the ones at the end because I have fewer people there. Why don't I give more weight to the ones at the beginning? And so what Frank Wilcoxon had in the 1940s had developed was the Wilcoxon rank sum test, but he adapted it for censored survival data. Remember that survival data, the unique thing it has is censoring. And so here, the generalized Wilcoxon test is nothing but the Wilcoxon rank sum statistic. If you took a course of non-parametrics, it's comparing the ranks in one group to the ranks in the other. And so the generalized Wilcoxon one is now comparing the ranks, but adjusting for censoring. And it's a weighted sum of the differences between these observed and expected ones. And he adjusts that by a weight. So it gives different weights to different time points I, and the variance now takes that into the weights. It's a little complicated, but the common weights that he said one uses, if I use the weight of one, I get the log rank. Here, the hyphenated it, unfortunately. It should not have been. This is a paper that had it like that. So the generalized Wilcoxon with weights of one is just the log rank. But other people propose different weights. Let's give more weight when the sample size is bigger or the square root of the sample size is bigger. Let's give more weight when the survival function is larger. And then this is another one a little bit more complicated. But when I'm early on and the survival is close to one, I give more weight than others. So we call these weights that are favoring early differences. Now, why would I choose one of these? If a priori, I think that my intervention is going to work better at the beginning, I may do this, but I have to pre-specify. I cannot go ahead and say, oh, I looked at the data, and so now I'm going to use the Guillen-Breslow one. No, you can't. That's why we force people, especially in clinical trials, to write down your statistical analysis plan, the SAP, before you start the study or before you look at the data, at least. People don't do it before they start the study, but at least before you look at the data, you say how you're going to analyze it. You're not at liberty of seeing the data and then deciding how you're going to analyze it. And because clinical trials are so important in potentially changing healthcare, the regulatory agencies force people to not only register your protocol, but register your analysis plan as well. And they will hold you to it when you send your results to the Indian Council of Medical Research or the FDA or EMA in Europe, or you want to have your paper published in New England Journal or Lancet or whatever, they will look at your protocol. They will demand, they'll go to that where you registered it. They'll look at the SAP that you registered and say, why did you not do this? You said you were going to do this. Why did you do that? Why did you do this? So be careful. You have to pre-specify things. All right. So the log rank test has certain assumptions, like every statistical test. So the censoring patterns are the same for the two treatment groups, is one of the issues that they worry about. And one little known one is that the hazard functions for the two treatment groups are proportional. So wait a second, the log rank test is non-parametric. It's just doing a 2x2 table at different time points. But when you're combining them across the whole time, it's assuming that the effect here is the same as the effect here, is effect here, effect here, effect here, to be able to combine it. Some people call it the poolability across time. So inherent in it, it's this proportional assumption. Now, if you don't have proportionality, what you're getting is an average effect. And if you still get it to be significant, then people celebrate because they think that's great. But when things cross, they cancel out. You don't have proportionality. If things are diverging or converging, they're not proportional. If early on you don't have differences and then you get them, they're not proportional. If early on you get big differences and then they merge, you don't have proportionality. Most of the times you don't have proportionality, but you're close enough. And we'll talk about checking the proportional hazards assumption. So the generalized Wilcoxon test allows you to handle the non-proportionality, but only if you expect it beforehand. If I know, oh, my intervention, I'm going to be doing, it's a counseling intervention in psychiatry, and I'm going to counsel this way or counsel that other way, and I have people randomized to different counselors to do this. And counseling takes 6 weeks, 12 weeks, but then the effects of it are not going to be noticeable till like 6 months. So early on, you're not going to get any differences. So you know that before. You know what you're doing. You know what the intervention is going to act like. So you don't expect that to happen. So don't give more weight to early on, give more weight to later on. But that's because you know it and you put that in your statistical analysis plan, in your protocol. We expect this for this clinical reason, for that clinical reason. And so therefore we are choosing to analyze this way. But if you don't say it, you can't do it. That's the only main thing. But both of them require that the censoring patterns for the two treatment groups be the same. All right. But then, as I said, people are not happy with just calculating a log rank test. They say, yeah, we got significance. No, we did not get significance. They got significance. They want to now say, oh, maybe I can get more significance if I do this or do that. I didn't get significance. Oh, what if I do this and that? Usually in a clinical trial, the analysis of the primary hypothesis is a crude one. It's unadjusted under the concept of intention to treat and without any adjustment except maybe for sampling design or in that case randomization assignment. But you don't adjust for covariance. You're supposed to have done a large enough study so that randomization will have balanced the arms of these covariates. And if you're not balanced, you will have to do that in a secondary analysis. And so secondary analysis are usually done, most of the times they're done, as a way of incorporating covariates in the model that may be due to imbalances at randomization, or because you want to sort of understand how they may affect or not affect the results, primary results. And there's two types of ways of incorporating covariates. One is called the accelerated failure time model, which models the survival times. And the other one is the proportional hazards models that models the hazard function. So the hazard function at time point t for the ith person or ith intervention would have some sort of form, and we'll talk about this in a second. And the survival time would take the log of it, because remember, those are very skewed, and we take that as the outcome and then model that as well with an intervention and some offset here. The accelerated failure time model is not very common. You don't see it. In most clinical papers, they don't do it. In some other technical papers and some disciplines, they may use it. But most people like the Cox model. Most people like the hazard function as a way to study the survival analysis or to model the survival analysis. So I'll talk only about the proportional hazards model. Now, there's not only one proportional hazard model, there's multiple. So for example, there are parametric survival models that are proportional hazards models. You don't see them very common, but there's the Weibull one, which is the most common of the parametric ones, where the hazard function is monotone, either increasing or decreasing, or So it's not constant. But you have the log logistic for unimodal hazard functions. You have the log normal. And for long-term follow-up, you have the Gompertz models. These are a little bit more complicated. Most standard software will have it, but many people that don't know that they're there don't look at it. It's also harder to explain because it's not very common. So most people don't use it. What most people do use is the semi-parametric Cox proportional hazards model. Why is it so popular? Because it depends on the exponential distribution. And that's one reason. And the second reason is that it's semi-parametric. It uses the exponential distribution for part of it. That's the parametric part. But the underlying hazard function is left unspecified, and people don't have to worry about it. And that's what makes it very attractive. This is the second most cited paper in statistics. It's after Kaplan-Meier. This is what got David Cox, the author of this, knighted by the Queen. Kaplan and Meier were Americans, of course, not knighted, but the British are knighted. So this paper appeared in 1972. And so since 1972, again, I didn't see it being used until 1975, no, even later, because I was a student in 1975. So we got it in the course on survival analysis. My professor was a professor from Poland, and she was in her 50s. She said, oh, there's this new thing called proportional hazards model. You read this paper. He gave me the paper to read. But it was not being used yet in the medical literature. But then it started being used because it's very, very nice mathematical. Let's look what it is. So what he said is, let's do one thing. The hazard function is what? It's the force of mortality, or that slope, that tangent to the survival function at a given time point, and it changes over time. So use lambda for the hazard, and it depends on time. So that's why T is there. But it depends on a bunch of covariates. X, age, sex, smoking, BMI, this, that. So the hazard depends. Treatment is also one of these. But he had the clever idea of saying that those two things it depends on can be separated into a part that involves time but no covariates, and a part that involves covariates and no time. As simple as when we first took our course in algebra in 6th grade, and we knew how to factor something, and we had a product, two things, that's all he proposed. Let's factor the hazard into two parts. Now comes the intuitive part that make it, that was the easy part. The hard part is understanding. So this is the hazard rate function. And he said, this is, we'll call it the underlying hazard function, which is how people are dying, how people are relapsing, how people are getting cured. This is something that is what's underlying in the rate of mortality, or your force of mortality, or your force of relapse, force of whatever that's happening to people that have this condition. I don't know what it is, but I don't care. All I care is finding out the effect of the covariates on it. And so now I'm going to have the way that the covariates affect your overall hazard is dependent in an exponential fashion. Why exponential? Because that's how things fail, as we saw this morning. Second reason is because the exponential function is not is memoryless. It has a constant hazard, and it is very simple mathematically. Because he says, I'm going to put the covariates as a linear function. So this x beta means beta coefficients of a linear model. So it's beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, etc. So you have a line, a simple or multiple linear regression. And so this third reason is that if I linearize it, if I take the natural log of the hazard, what happens? This now goes back to the trigonometry in high school. Then this, it's the log of a product, is the product of the logs, the sum of the logs, sorry. So this is the log of this, plus the log of e to the x beta is just x beta. So now this is a linear function in the covariance, and this is just the offset to the beta. And I don't care about this, because whatever it is, what it is, I just want to know what is the impact of the intervention. That's one of the covariants. What is the impact of sex? That's it. I want to study the effect of this on the hazard. So you remember this time to event analysis, the graph. I have the graph again here. Now I have two groups, not just one group. So I can get the hazard in group A at this time point and at this time point, the hazard in group B at this time point and at this time point. And I can take the ratio of the hazards here and the ratio of the hazards here. These hazards look pretty similar. So the ratio is likely to be 1. Here, they don't look similar. They're not the same. So the hazard rate ratio here is different than the hazard rate ratio here, right? Visually. Well, that's not good for proportional hazards. Why? So the hazard rate ratio, I can get it at time point 1 and at time point 2 with this. But when I'm modeling the hazard with the Cox model, things behave nicely. Let's see how. So if we have two groups, A and B, the ratio of the hazard functions is what we had there, the ratio of the hazard. And it also will vary over time, which we just saw in the previous one. So, but the mathematical impact of Cox's assumption for this semi-parametric form, by saying that your hazard function follows the specific product formulation, is that when x is fixed, the ratio of hazard functions will be constant over time. And so the proportionality assumption makes that hazard rate ratio to be the same at every time point. And that's what you get, is that the hazard rate ratio that varies over time and varies by x, under the proportional hazards assumption, only varies by x. The time part goes away. So that lambda naught t that I did not know doesn't bother me. It just poof, disappears. I'll show you mathematically and convince you that that's true. So let the variable be x1, 0 if male, 1 if female, and x2 is some constant value k. So maybe age equals 25, whatever. So for females, the hazard for females at time point t, when x2 is equal to k, is going to be what? It's lambda naught t, right? That's the unspecified part. And it's e to the beta 1 for x1 multiplied by 1, so it stays at beta 1, plus beta 2 times k, because that's what x2 is equal to. Everybody get that? So the hazard, skipped one little step here, and that's probably why. So the hazard t depends on x1 and x2. Okay, and so this is lambda naught t e to the beta 1 x1 plus beta 2 x2. That's that x beta written out like that. But what I'm saying is for females, x1 is equal to 1. And this is at x2 equal k. So now if this is equal to 1, That's this beta 1, and this says that. So that's what I have there. And for males, x1 is equal to 0. And x2, now we still have k. So that's lambda naught t, e to the beta 1 x1 plus beta 2 x2. This is 0, so this is gone. Right? So we just have that. That's what I have over there. But I'm not interested in the hazard of males and females. I want the hazard rate ratio, the ratio of those hazards. So I take the ratio of those hazards, and now I go back to simple math. The hazard rate ratio is now divide one by the other. What happens? These cancel out, and e to the beta 1, e to the sum of something is the product of those e's. And so e to the beta 2k and e to the beta 2k cancel out, and I'm left with e to the beta 1. And what is beta 1? It's the coefficient for sex. So now the hazard rate ratio of females to males is obtained like this over time, over the entire survival time period that I've studied. I only have to report one. And the hazard ratio is interpreted just like the risk ratio or relative risk or odds ratio. If it's greater than 1, then females have higher hazards than men. If it's less than 1, females have less hazard than men. If it's equal to 1, females have equal hazards than men. Careful that they have equal hazards, not equal risks. And in the papers you read, people are sloppy with terminology. They have modeled hazards, they've gotten the results in hazards, but they say it's the riskier, or there's a higher risk for this, for that group, or that group. But if they want to be correct, they should say there's higher conditional risk. Conditional instantaneous risk overall is higher. That's why you have the convenience of one word hazard, but then people don't understand what you're talking about. So they use risk, and then they call it trouble. It's crucial. And yeah. Oh, time for lunch. All right, so we'll come back to the proportional hazards assumption in estimate. But I'll end with one example that's funny, because this constant hazards give you that survival that looks like it's exponential. But suppose you're crossing a wide avenue like in New Delhi with a divider, and you have the footpath, and you are trying to get to the other footpath, and you have 3 lanes, you have a median where you can stop, and you have another 3 lanes to cross on the other side. And so what is your hazard? Your hazard is very low here. It's maybe a little bit higher at the median because a car can come and kill you there, but not so high. When you're crossing, you are at high risk, conditional of getting it. So hazard goes up and down. Here you have maybe a little bit smarter person, here less smart person crossing the road. So that depends on the smartness of the person, which is your hazard. But then their survival functions are like this. These are proportional hazards that I have here. But not the hazards are proportional. We'll see them